In this video, we're looking at vector-valued functions again. In particular, we're going to look at an example of sketching a space curve. So just as a recap, recall, a vector-valued function r of t can be in 2D or 3D. It can actually be in n dimensions, as many dimensions as we want. In 2D, it looks like this. It has components x of t and y of t. And as t increases, we can think of this as tracing out some curve in space, some curve in the plane. So this particular r of t is taking a point t and it's mapping it to a location x of t, y of t in the xy plane. So there's going to be some plane. Here's y, here's x. And as t increases, I'm going to travel along some curve. And r of t is a vector that points to a particular point on the curve, and this point is given by this functions of t, x of t and y of t. R of t starts at the origin and it points right there, and it's like a you are here arrow telling you exactly where you're located. This is the same thing, but just in 3D instead of 2D. R of t might be a vector-valued function that maps to a point x of t, y of t, and z of t. So we're taking a real number, some real number, well, we're going to take some number in the domain of R, which is a subset of the real numbers, and then we're going to map that to a point in three-dimensional space. So we're going from R into R3. So what we would see here is we've got x of t here, or we've got x-axis, y-axis, and z-axis. And now as t changes, we get some curve. Who knows what it looks like. But as t changes, we get something that looks like this, and we're in three-dimensional space. And r of t starts at the origin, and it points to a particular point, and it says that's where you are. You're located right here, and your location is given by x of t, y of t, z of t. So generally the r's are not drawn, you're just drawing the curve in three-dimensional space. Now technically this can go to n dimensions. So we could have x1 of t, x2 of t, x sub 3 of t, x sub n of t, and this is still going to take some real number in the domain of r of t, and it's going to map it to a point in n-dimensional space. Now, I can't draw that, but we're going to think of it as one-dimensional. As t takes on this one value, or as t takes on one real number value, we're going to get ordered n-tuples in Rn. In the last video, we did a lot of sketches like this. In this video, we're going to try to do sketches like this. You can see even from my picture, it's hard to tell. It's hard to give it that sense of a third dimension. But we're going to do the best we can, and in order to do that, we're going to use surfaces, the surfaces that we studied in the last section. But before we do that, one last thing. We're thinking of r of t as generating a curve c. So this is a plane curve because it's in 2D. And the plane curve consists of all of the points on this curve, as well as the parametric equations that give us that curve. So the plane curve c is generated by x of t, y of t. Even if you got exactly the same curve, or exactly the same collections of points, it would be called a different curve if we had different parametric equations. And the same is true here, but since we're in three-dimensional space, we're going to call it a space curve, C. But since t takes on a single value, we just get this one-dimensional thing. It lives in three-dimensional space, but it's one-dimensional. It's not a surface. It's not 2D. It's just a 1D. It's just a path in 2D or a path in 3D. Or over here, can't draw it, but it's a path in ND. All right. So that in mind, let's try to do this. Let's look at this example. We want to try to sketch this R of t, and it's in three-dimensional space. Now this is difficult to draw. This 3D anything is difficult to draw, but we do the best we can. One thing that helps is sketching the curves on surfaces whose equations we know. And generally, we're only going to look at surfaces which are variations of the quadric surfaces we studied in the last chapter, as well as cylinders, of course planes could be a part of it, and spheres. I'm not going to ask you to draw anything too exotic. We're just going to use the surfaces we know. So I've got x of t, y of t, and z of t. And we're told that r of t is mapping to this point in three-dimensional space for every t that's greater than or equal to 0. So let's just plug in 0 and see what we get. When t equals 0, we get 4 times 0 times cosine of 0, so that's 0. And 4 times 0 times sine of 0, clearly also 0. And 4 times 0, which is 0. So it's a pretty boring vector, not much going on. I get the 0 vector. So at t equals 0, we're at a particular location. It's x of 0, y of 0, z of 0. And that location is the origin. We're at 0, 0, 0. And the question becomes, okay, well, what happens to this as t increases? When t equals 1, where are we? And what does it look like? And when t equals 2, where are we? And what does it look like? So we want to keep all of that in mind as we're sketching this. Now, one thing that we do here is exactly what we did in 2D. We're going to eliminate the parameter t. But remember, this is a curve. It's not a surface. But we're going to find a surface that our curve is lying on, if that makes sense. Just to show you what I mean, notice you get an x of t that has a cosine in it and a y of t that has a sine in it. Do you remember what we did whenever we had a cosine and a sine in our parametric equations and we wanted to eliminate t? Well, remember we said we don't want to take the arc sine of something, and we don't want to have to take the arc cosine of something, because even though algebraically all of that's fine, there might be some domain and range issues, but generally that's okay. Problem is, I don't know what it looks like other than the typical inverse trig functions. Some composition involving trig functions and inverse trig functions. It's not obvious what that graph looks like, not with everything that we've studied so far. So we want to do something else. Remember what we said in the last video. If we have a cosine and a sine, often we get sine and cosine by themselves and use the Pythagorean identity. This one comes up over and over again. I'm going to list the other two as well. They're a little less common, but they're also important. Sine squared of some angle, I'm just going to use a for angle. Sine squared of some angle plus cosine squared of the same angle equals 1. And if I take this and I divide by cosine squared, sine squared over cosine squared is tangent squared. Cosine squared over cosine squared is 1. And 1 over cosine squared is secant squared. And if I take this and I divide by sine squared over itself is 1. Cosine squared over sine squared is cotangent squared. And 1 over sine squared is cosecant squared. So we use these a little bit less often. We tend to use this one, but these three actually come up pretty often in all of our calculus sequence. So this is the one that is applicable here. I've got a sine squared and a cosine squared, and I've got a cosine and a sine, so it makes sense to use that one. Okay, so in order to do that, I'm going to solve x of t for cosine and solve y of t for sine. And to eliminate all the extra t's, I'm just going to make the dependence on t implied. So we have x equals 4 cosine of t, and y equals 4 sine of t. If I'm solving this for cosine, I get x divided by 4t equals cosine of t. And here, I'm solving this one for sine. getting this by itself, I have to divide both sides by 4t. I get y divided by 4t equals sine of t. And then according to this identity, if I take those two pieces and square them and add them, I should get 1 because of our Pythagorean identities. So sine squared plus cosine squared is 1, and sine of t is y over 4t, and cosine of t is x over 4t. You might be saying, Miss Townsend, that did not eliminate the parameter t, and you are absolutely right, it did not. I've got y squared over 4t squared plus x squared over 4t squared equals 1. Still have t's in it, but I did get rid of my trig functions, which is nice, so it is a little simpler. And I can multiply both sides by 4t squared, and it's the quantity 4t squared. I changed the order a little bit, but it's the same. Okay, the question is, here's x and here's y, how does this relate to z? Well, that's convenient. Z equals 4t. So that's actually z squared. This is z. That's what we were told. Z is 4t. So our curve, and it is a curve, lies on this surface, the surface given by x squared plus y squared equals z squared. Now remember, t is greater than or equal to 0, and if t is greater than or equal to 0, that means z must also be greater than or equal to 0. So you've got x squared plus y squared equals z squared, and let's add this restriction, z is greater than or equal to 0. Now it doesn't quite look like one of my quadratic surfaces yet, but I notice I've got all 3 variables squared. I'm going to manipulate it so all 3 variables are squared and on the same side. So I've got that. You guys recognize it? 3 variables squared, 2 positive, 1 negative. The other side is 0. I hope you said that's a cone. If you did say it's a cone, you're absolutely right. This is an elliptic cone. That is not our curve. That is just the surface that our curve is lying on. And it's going to make it a little bit easier to figure out what's going on. Well, we know that this cone opens on the z-axis, and since z is greater than or equal to 0, we just get the top half of the cone. Alright. Now the question becomes, well, what happens as t increases? Well, as t increases, z increases. And we're going up in the x direction and y direction following these parametric equations. Just to get some sense of what's going on, I think I'm going to substitute in some values of t and then see if we can graph it and see what's happening. So let's create a little chart. I want t, I want x of t, which is 4t cosine of t, y of t, which is 4t sine of t, and z of t, which is just 4t. I'll probably do that one first. So let's let t go from 0 to 2 pi. We'll just do multiples of pi over 2 because we're comfortable with those. For z, you just multiply each of those t values by 4. 0 times 4 is 0. Pi over 2 times 4, and that's 2 pi. Then we get 4 pi. Then over here we get 6 pi. 2 pi times 4 is 8 pi. Meanwhile, when t is 0, this is 0, and this is 0, so we are at the origin. And when t equals pi over 2, out front I've got a 2 pi, and then I have cosine of pi over 2 here. Remember, cosine of pi over 2 is 0. And sine of pi over 2 is 1, so I end up with that. 2 pi times sine of pi over 2 gives me 2 pi times 1, which is 2 pi. Over here, when when t equals pi, z equals 4t equals 4 pi. So this is 4 pi times cosine of pi. Cosine of pi is negative 1. Sine of pi is 0, so that's 0. All right. At 3 pi over 2, all the odd multiples of 3 pi over 2, or all odd multiples of pi over 2, cosine is 0, so that's going to be 0. Sine of 3 pi over 2 is negative 1, so we're going to have this, which is 6 pi. 6 pi times negative 1 is negative 6 pi. And then at 2 pi, sine of 2 pi is 0. Cosine of 2 pi is 1. So we've got 8 pi times 1, which is 8 pi. Do you see what's happening? Maybe it's a little bit difficult to see. But we start here at 0, 0. And then sometime later, we're at z equals 2 pi, y equals 2 pi, x equals 0. So we're right here on the curve. And then sometime later, after that, we're at z equals 4 pi, and x equals negative 4 pi. Ooh, that's hard to draw. I think it's on the other side of this cone. But y equals 0, so we're in the the xz plane. Oh, it's so hard because this line on the cone looks like it's the negative x-axis. But okay, I'm having difficulty drawing this. But what you're going to see is you're going to see a spiral. If that 4t and that if the 4t weren't here, if I had just x equals cosine of t and y equals sine of t, we'd just be going around and around in a circle. I'm doing something similar, but I'm starting at a circle of radius 0. I'm starting at the degenerate circle. And then as t increases, we're spiraling up and spiraling up and spiraling up. And so I think this is what it's going to look like. It's going to be something like this. And you've got to imagine some of that is on the back half of the cone. Okay, difficult to draw, but this is our curve C, plane or space curve C generated by r of t, and r of t has components for cosine of t, or 4t cosine of t, 4t sine of t, and 4t for z. And this is for t greater than or equal to 0, and it's just going to keep going up. As t increases, we go up the spiral. So we keep going this way. All right. That's what we've got. Okay, that was a lot. Let's talk about what we just did. If somebody asks you to sketch a space curve. Generally, the way we're going to be able to sketch a space curve is we're going to eliminate the parameter t by showing that our space curve lies on some surface. Now, in this case, because this had a cosine and a sine in it, we were able to use the Pythagorean identity to get rid of the trig functions. And then we were able to do a little bit of algebra and see that we had a z over here. So this ended up being a cone. But I want you to see that even when we've done all of this, we've eliminated the parameter t. R of t is not giving us the whole cone. A lot of students think they get to this point and they sketch the cone, they're like, R of t is this, it's the cone. It's not the cone. It's just a path on the cone. And to figure out what that path is, we really have to think about what happens here. Now, plotting these points, I thought it might help, but when I was trying to graph it in 3D, it was still difficult to visualize. But I know when I'm saying x is 0 y is 2 pi and z is 2 pi, then I'm over here in the yz plane at 2 pi. Here, I'm back in the xz plane, where x is negative 4 pi, so that's behind us, and z is 4 pi, and y is 0. And so this list of values, to me, represents this curve, but it might not be so obvious to you, especially when you're just starting out. Don't be too hard on yourself if you're like, I don't look at that and see that. That's okay. But I do want you to recognize this pattern. Whenever you see cosine of t and a sine of t in your parametric equations, it's very similar to what you saw way back in trig class. As theta increased, you're going around and around the unit circle, right? This was cosine of theta, sine of theta. We weren't talking about vector valued functions back then, but as theta increases, we go this way, right? We're traveling along this path. It's very similar. So whenever you see that cosine of t and sine of t, there's usually some kind of circular motion. Because those cosines and sines were also multiplied by something, this 4t, which is getting larger and larger and larger, we didn't just stay on a single circle. We were on this spiraling path where we started at 0, 0, and then it started going out and out and out and out. And every time it went out, the z value also went up. So we end up with something like this sort of spiral on a cone. I hope that makes sense. When you're doing this for the quiz in our class, just do the best you can. But please know that after you've eliminated the parameter, it's going to be one of the surfaces that we've talked about in the previous chapter. And then you're just going to be sketching a path on the surface. And this pattern that comes up with the sine and cosine is one you can count on. It just means things are going around and around. If the cosine is associated with the x and the sine is associated with y, it's going this way. If you flip them, we can prove it. I'm not going to prove it in this video, but we could. If you flip this so that the x is given with a sine of t and the y is given with a cosine, instead of going counterclockwise, it goes clockwise. But I won't be proving that in this video.